another contractor, an ICI Orica, and he worked with Orica internationally too in Britain for a time. Barry was appointed the Chief Technologist of the Cooperative Research Centre for Greenhouse Gas Technologies. That's a big mouthful. The short for that is CO2 CRC, so I'm sure Barry will refer to that. And he was as Chief Technologist from 2003 to 2014. He then founded a startup company, UNO Technology, in 2014 to commercialize the intellectual property of this CRC, which is looking at reducing costs for low-emission fossil fuels power generation stations, so retrofitting or putting in a new plant. Now, Barry is a Fellow of the Institution of Chemical Engineers and an Associate Professor at the University of Melbourne, and he's lectured in the Chemical Engineering Department since 2001. Now, the government response to the Finkel report is expected before the end of this month, and it's arguably the most important policy setting that will be made this year. Please join me in welcoming Barry to address us on carbon capture and storage and what might follow Finkel.
Thank you very much, Ben. Please, if you can't hear me, let me know. But I'll go back to my thespian days, and hopefully I can project well enough for you all to hear. So, thank you very much, and thank you for inviting me here today. And I hope I can give you some background into this area, in the energy field, in some things that are often talked about in the media, the Finkel Review, the NEM, and so on, and particularly in the area of carbon capture and storage, which is about low emissions fossil fuels. So there's a lot here. I'm not terribly au fait with the mix in the group, but hopefully it doesn't get too technical, and we don't. There's a few good animations and so on, and we've actually got a YouTube which Philip will put on in a couple of minutes to explain things in different areas that I'm not as familiar with. So thank you very much. And so the things I'm going to talk to you about, and a lot of things around climate change affects a lot of these things, and so I'm going to give you a bit of introduction to that, an introduction to what carbon capture and storage is, perhaps a little bit different to the way it's talked about in the media, a little bit of what the energy system looks like, the NEM and all of those features. And some of the things I really want to get you across here is to understand some of the things you'll be reading in the media, that to actually put it into perspective in a more balanced way. So I'll cover that, a little bit about the Finkel Review and some concluding comments. So in the area of climate change, one of the things that drives this is actually the United Nations Framework Convention for Climate Change. And that overlays all the things you hear, IPCC and so on. And in fact, this convention was signed up to all countries way back in the 90s. So it's not a matter of Kyoto, that was subsequent to this. It's interesting to read some of the things that underpin that, and I won't, you don't need to read the details there, but there are really three key elements about stabilising the concentrations of greenhouse gases. There was no talk about specific emissions at that stage, and saying that recognise that there is a level at which that will be a problem. It didn't actually specify it in those early days, but it also said, but we also have to do this in a background of ongoing economic development. So in some ways there's a trilemma, although I won't say it's not what is referred to as the energy trilemma. So when I started involved in this, these are the sorts of things that I was looking at. This is 15 years ago, okay? Things that were, to me, entering the space, saying, what are the impacts? What's happening with temperatures and so on? And this is one of those. It's old information. I'll update that shortly. But it's basically saying here's a temperature measure which shows over the last millennia what has happened with the temperature profile. And then you'll see at a point which neatly coincides with the Industrial Revolution where temperatures start to really spike. And then you have things like the similar sorts of data from on CO2 and so on, you start to see an alignment of those. So to me at the time, it was very much a matter of what do we need to do, at least in terms of an insurance policy, to say how we would deal with this if this becomes a problem. So I'm not an expert in these sorts of things, but so I pulled up a YouTube video which has only been released in the recent times. It tries to pull all of these things together. So hopefully that can help to explain it better than I possibly can. And we'll get this running. It's put together by a group at Melbourne University and other. So not sure we'll have the audio for various reasons. Basically saying here we are with the, not to overlay this, let's look at the data around the movement of CO2 and how it affects the world. This is saying if we didn't have an atmosphere and the CO2 wasn't there, we would have a very cold climate, minus 18 degrees Celsius. But there is a balance between the CO2 and the climate. Over many years, it's a pity you can't look at the audio. This is basically saying is that we can track these by looking at ice cores. You're looking at stuff about Antarctica. And this is the measurements of CO2 levels and temperatures overlaying, going back hundreds of thousands of years.
These are the core samples.
These are core sample information. So there's core information, core sample information, CO2, temperature profiles. This is going back when civilization started. Here we have particular periods where the CO2 was high and temperatures rose by that sort of level, up to 9 to 10 degrees. So going backwards, ice ages, once again, this would be much better if you could hear this. We had ice sheets forming and going right across Europe to a kilometre deep in this period. And as you move forward, things started to warm up. These are the ppm of CO2 over here and the temperature here. And so there was a natural order of increasing temperature of CO2 over that time, of about 35 ppm per 1,000 years. So now we move to the modern era, or here we had very few people way back at the start of the 18th, 20th century. Then other things happening, Industrial Revolution, and then we start to see spikes. And it wasn't until, the date escapes me, but somewhere in the 1930s, there was confirmation of this correlation of the temperature and the rise of CO2. And there's where we're getting to. We now have this sort of temperature, this sort of CO2, and we've got this trailing temperature catching up with it. So rather than 35 ppm, we're now getting 35 ppm rising in the last 17 years. Never seen in that record previous. Now we have significant numbers of people, more than we had way back when, and these, through our energy usage and what have you, was accelerating the impact. Suggestion here that we're at this low levels, but when we get to here, you start to see very significant impacts. In this case, they're referring to the rise of seas and the impact on where our coastal populations are most intense. And so there are various scenarios that the IPC has looked at in terms of low and high, and they're now codifying the sort of levels that first UNFCCC document. Yeah, sorry, thank you. It's a video. I'm not the best person to explain that. The voiceover that is available. I'm sure Phil can direct you to that YouTube to have a look at. It's basically saying there is a significant correlation, which has now been more significantly. That's the YouTube reference. That says, look, things that are going to have to be dealt with in some way. So please don't try and read this, but what I'm showing here is that the IPC and its efforts is looking at many, many scenarios of the sort of pathway of emissions reductions and then correlating that back to limiting temperature and CO2 increase and working out how that can be best derived to actually limit the potential impacts going forward. And we're not talking about doing this thing in the next 10 years. There's something that has to be sorted out over this coming century and into the second half of this century. This group here is another, this is from the IPCC, you can pull that up if you like, but they've translated a lot of these different pathways into CO2 scenarios and then back into how much low emission energy would we need as the primary source of our operating our community. And this then translates to the sort of changes that percentage has to be from, say, 2030 all the way up to the end of the century. So the information is there that you can see. So it's moved on somewhat in the last 15 years. And the suggestion is that in order to create this a more stable situation, we do need to have deep cuts. It's something that we need to have a number of different technologies at our hands to provide that change, certainly in the energy space. The goal is very challenging. It's international and it's, what I say, century long. It's decades, many decades long. The IPCC, coming back to my basic discussion around CCS, IPCC has included this in the low emission energy mix. And interestingly enough, if we do believe we do have a carbon constrained world, and the world has made a lot of moves that way, whether we like it or not individually, that's where a lot of things are moving. In a carbon constrained world, if you don't have something like carbon capture and storage, there is no future for the ongoing use of fossil fuels, because that's where the predominant CO2 is coming from. So that's a bit of an overview of climate change, as best I can do it. And how does this relate to our energy mix and our future? So really, you would have to have a greater mix of these things. Yes, there will be needs for some renewables. You need to switch to lower intensity fuels, greater energy efficiency, biosequestration into carbon sinks of forests, etc. And then the ongoing use of our low-cost fossil fuel in a low emissions way using CCS. So, what is carbon capture and storage? It's about capturing the CO2 and from wherever it's produced. Is that a fossil fuel power station? Is it an industrial plant, chemical plant, making LNG, any other material? So you take that and you purify it. You compress it to a liquid-like form, and then that allows you to transport it quite readily, particularly in pipelines. You then take it to an injection site, a geological storage site, and then inject that into that formation. And it's not a matter of putting it into a dome or a hole deep in the ground, it's actually putting it into rock. So actually injecting this into porous rock. Just like oil and gas comes from porous rock, it's going back into porous rock. It goes in, it moves, it migrates, fluids in the Earth's crust move, water is predominant fluid in the Earth's crust, and as you're putting it down you have to look to see where it is and say where you hope it to, and then to have it permanently trapped in that location. And this is an interesting thing, is it goes in as a mobile fluid, it dissolves into the water over time, it becomes more dense and then stops to being mobile in the sense of buoyance, movement, and it then starts to carbonate. So it actually starts to turn into rocks. The rocks form carbonate. And the CO2 cycle actually does that. But what we're doing it is in situ, in a geological formation. I'll come to a little bit more detail about the storage, because that's probably a more difficult thing to understand. But in going through those steps, here we have carbon capture. So here we have a CO2 gas, in this case it's coming from a power station, it might be about 4% up to 15% carbon dioxide in this gas. So we pass it through a device which connects it with a liquid. The liquid uptakes that CO2 preferentially and removes it from the gas, and the gas goes back out to the atmosphere. The CO2 in this liquid goes to another device called a stripper or regenerator, and it's heated up and the CO2 comes out, and now you have pure CO2. So you've taken it from 4 to 15% to 100% CO2. Now it can be moved and taken to storage. This, by the way, is a commercially available licensor, one of my competitors, if you like. And this is what it looks like in real life. This is a plant I visited a few months ago in Houston, one of the largest energy producers. I think it's the second largest power plant in the States. It has both coal and gas-fired power. And here's the capture plant that I just described. Blue gas comes in here. This is the absorber. This is the stripper. You have a compressor here that then sends it off out this way to storage. Big plants for the capture plant as well as the power plant. And Ken said to me, make sure people understand these things take a while to put in place. Anything in energy is going to take several years to actually get into fruition. So this is the capture side. Now, the storage that I have referred to before, this is what you need. You need a porous rock. We talked about that sedimentary rock, that sandstone. You also need what we call a seal rock. So you've got this porous space, and then you want a cap on it. So you want a cap to keep it in place. So you need these pairs, and then you inject it into that rock. So let's have a look at this rock face. There's the reservoir rock and the seal rock. And so what happens at a microscopic level, here we have the grains of rock and you see all the spaces there. That's the porous, that's where the CO2 goes and the liquid goes. And then this one has very limited pore spaces, and so that keeps it in there. And that's what's kept oil and gas reservoirs intact for millions of years. So, but I'm not going to go down to Half Moon Bay and try to inject into a cliff face anyway. Okay, this just shows you what you can see when you go around, and those geologists of you would think this is wonderful. But what we do is this is repeated. These pairs are repeated over time. Sedimentary rocks have built up. And so what we're looking for is these pairs at a depth of over 1 kilometre. There's a reason for that. It's because to keep the fluid as a liquid, the CO2 as a liquid effectively. And you inject it into these reservoirs at that depth. And that's what's there. That's why the IPC says that this stuff can be maintained in those locations for a very, very long time. They're thousands of years. By the time it gets to that, you've actually gone through a carbonation cycle with this CO2. So that's the geological storage. And just a little bit of an animation here to show what that looks like. You start to, whoops, there we go. You're injecting, and the red bit, the Kalman bit, is the CO2. It goes into that reservoir and fills up the pore spaces, and then it's maintained by that seal. That's just one example. There are many such examples. So you end up having this sort of, this is an aerial plan view of of that structure. And so there are many proven seal potential of these sorts of reservoirs, and many opportunities in Australia, and other sorts that actually have very, very large storage capacity over potentially hundreds of kilometres of aerial space. So is this being done? Yes, it is. This is a depiction of the Sleipner CO2 storage project in the North Sea. It's been going since 1996, had its 20th anniversary last year, injecting 1 million tonnes per annum into these reservoirs. What you see here is the CO2 from on-seismic, but it's in matter of production of natural gas. The CO2 that comes out is removed and actually put into another somewhat higher reservoir. So this is being continually monitored and shown to be successful. So this is the first major one. It's been done for years. Here in Australia, we've done a lot of these work, more in the smaller scale projects. Various of these are pilot capture plants and so on. Many of these in Victoria, which I've been involved in the majority of them. Two I'll particularly point out, these are storage projects. The CO2 CRC still operates. a project in the Otways where there's effectively injecting. It's more of a research facility. And the other one I'll point out is Gorgon, which is the Chevron LNG project that Off talked about. They, in the very near future, will be starting to inject, and that will be the largest CO2 storage injection in the world. They're looking at 3.5 to 4 million tonnes of CO2. So there's a lot of activity. The CO2 CRC Otway project, as I said, a lot of monitoring, research and so on. For any of those who are interested and go down this way, it's halfway between Warrnambool and Port Campbell. They have a visitor site, you can go. Quite an unobtrusive place. It's on a dairy farm. The farmer actually is the person who helps to operate and maintain the site in that area. So, that's what about what's happening on this space most recently? So the GCCSI, which was set up by Kevin Rudd a number of years ago, still in existence, based here in Melbourne, has offices all around the world, collates and advocates a lot of this work around the world. So this is a slide from the General Manager from Asia Pacific, Alex. You won't be able to read these in detail, but the blobs are basically all of the CCS projects, the large CCS projects in existence around the world. And we've got 17 such large facilities injecting very large quantities of CO2, 5 in construction, making up a total of 22. So by the end of 2018-19, there'll be 40 million tonnes of CO2 being injected. And these are just a timeline of those that are happening in the last year. And I've just pulled a couple of them out. This is an interesting one in Abu Dhabi where they're actually capturing CO2 from a steel mill. So it's not just energy, it's any CO2 source. CCS is a CO2 reduction technology, so it can reduce the CO2 that comes naturally from coking coal where you're reducing iron ore. This is the one I showed you before. It's about 1.4 million tonnes a year on the back of a 250 megawatt power station. And this one finally is on an ethanol plant. So it's a biological, taking corn, producing ethanol, that produces a lot of CO2, and that's capturing in the order of 1 million tonnes a year. So a fair few of these things going on, and their costs are coming down through getting more of these, and I'll show you a little bit more of those shortly. There's a lot of improvement in this, and any suggestion that this is not an active technology in terms of improvements in cost and reducing costs doesn't know the facts. And there are some other technologies that are actually really quite step out, and I visited those also in Houston a couple of months ago. And just one example here in terms of how the costs are reducing. This is what I call N=1. This was the first plant, a retrofitting capture to a lignite-fired power station in Saskatchewan. I went to the opening of that, and N=2 is the one that we talked about before. This group reckoned that as soon as they build it, we're going to take 30% off it. Right, they then went to a different company, built this one. They had a 20% cost reduction on that, and they would say they were going to have 30% reduction at the next time. So things are, just by learning, by doing, is going to be very high cost reduction pathway. So it can actually become quite readily done at large scale and at ever increasingly reduced costs. Ever reduced costs is probably better. So that's CCS. Now, how does this link into power generation, which is the thrust of our discussion? So here's a bit of power generation 101, as I call it. And I'll just quickly show you, for those who are interested, this is a typical coal-fired power plant, often called a pulverised coal-fired plant. And not being a power plant person myself, I crudely say that what they do is crush a little bit of coal, blow it into a box, burn it, boil some water, and spin a few turbines, because that's just what happens. Okay? Coal goes in, burn it, heating water, water comes down, spins the turbine, generator, power. The gas, which is where all the CO2 is, goes through other treatment of various sorts, but this is where you would take that flue gas and put it through that capture plant and remove the CO2. So that's one form, a lot talked about. And I'll mention something later you've seen in the press, HELEs, H-E-L-Es, high efficiency, low emission power plants. That's been talked about. And all that is something that operates at a slightly higher pressure and a higher efficiency. From a gas perspective, we produce a lot of power with natural gas, and you've heard a lot about that. So what we actually hear is a jet engine. But seriously, these jet engine. You've got a compressor and a turbine. Gas comes in, the fuel in this case, not gas, a liquid jet fuel, but the compressor on a similar shaft sucks in air, compresses it up, combustion chamber, the hot gases go out, spin the turbine, exhaust goes out, and you've got the power. It's called an open cycle here because the emissions go straight out, no particular, very hot, also high in CO2 actually, but very good for peaking plants. These can become much more efficient in what's called a closed cycle plant. Same front end, same jet engine, generator, but what it does to make it more efficient is it takes this very hot gas and actually does what the pulverised fuel plant does. It heats water, boils water, spins turbines, and get extra power from a steam turbine. And so more efficient, a little less flexible than an open cycle, but that's how it's done. What else are we talking about in the debate about energy, and particularly low emissions energy? Renewables. Largely, the first, what's often talked about, and most likely often talked about, is intermittency of these renewables. Wind is the cheapest form, but it's only available based on its capacity, say 100 megawatt. It'll only produce the equivalent of 30 megawatts, 30% over the year, because the wind doesn't blow, it's blowing too fast, or what have you. And so, so that's one thing to remember about renewables. Same thing with solar, very lower online time, and I'm sure lots of you have got these on your roof. And the way these costs are coming down are what they call economies of manufacture, because all of them are like little solar cells that are made into bigger solar cells that are put on your panels that are put on your roof, are then taken out and put into acreage for grid scale power. So by making lots and lots of them, the costs come down, and that's what we're seeing, as well as some technology changes, clearly, but largely that's what's happening. And in the wind turbine case, this pod at the back is where all that generator stuff sits. I just thought that was interesting to say how it's self-contained in that way. I'll use the term firm renewables. This is about making the renewables more reliable and available and equivalent, if you like, to traditional baseload power plant. It's sort of available 24/7. And how do you do this? Because it's only each of them, the fundamental generators are only have a 10%, 20%, 30% uptime. You have to provide more of those generators, and to provide, when it's generating, to put that extra power into some form of storage, whether it's batteries, it's a thermal, chemical, hydraulic, something like solar thermal, which this is a concentrated solar thermal plant, but it's not free. You have a lot more generators, a lot more panels, a lot more wind turbines, and also more batteries and inverters and all sorts of other things. So you have to realise the differences between these. So we've now got all the information in terms of what CCS is, how this comes back into power, but how does that then start to affect this whole discussion about the energy trilemma, and what is it? It's about getting affordability, reliability, as well as low emissions. In Australia, we have a lot of conflicting positive and negative influences on this, and I'll describe those. One is the NEM itself is somewhat negative in terms of energy trilemma, and that might sound implausible, but I'll explain that. How we actually talk about things like low emissions and clean energy is another thing. The fact that we've introduced policies which actually don't support an energy trilemma, and the way it's talked about and the community is exposed to these, the way we compare the information that's around is actually not helpful to have a community support to actually reduce or create an energy trilemma. And I guess it's not surprising, I think there are some positive opportunities from the CCS to deliver those. If we address some of these issues, you'll find this would come into a sensible part of the mix. So, national electricity market. For those of you who are not familiar, you hear the term. It's a very large machine, if you like. It's an interconnected system. It goes all the way from Cairns, all the way across to Adelaide, down to Hobart, and links all of those. It's one of the largest electricity markets in the world. It doesn't include Western Australia and Northern Territory, but it connects all the generators and all the users. Has $12 billion of electricity traded, 10 million customers, 40,000 kilometres of transmission lines, 47 gigawatts of capacity, and it itself is contributing somewhere in the order of 162 million tonnes a year of CO2 through that, how it's created. It was designed to provide two things: reliable and cheap power. Emissions were not even considered, so that's why I said it's not designed to create a good energy trilemma. So in recent times, it's worked well for a while, but we've had problems of affordability, reliability. We've had interconnectors go down, Victoria, South Australia, Tasmania, Victoria, statewide blackouts in South Australia in September last year. So that led to what then is being termed the Finkel Review. The COAG Energy Council in October last year set up the Finkel Review to address these problems. And they issued a preliminary report in December last year, and have now issued a report after requesting lots and lots of submissions. Got 216, I think, submissions to the Finkel Review. So that's the background of how this all comes together. So the question of terminology, I just say, if you're thinking about emissions and reduction of emissions, and people think about this generally overseas around clean energy, it is all about CO2 reduction. Unfortunately, here in Australia, it actually tends to be polarised only towards renewables and energy efficiency. It doesn't include any other balanced, what I call technology neutral solutions. And that's not to say renewables aren't important, they are. It's part of that balanced mix that we need. And so the IPCC in fact says that you need to be considering all of these in the future energy mix. And the problem is that the legislative drivers, the NEM, is there to do those two things, but the cheapest, most reliable power is high emissions. And then the energy incentives, if you like, for low emissions are fine, but they support the cheapest renewables, which are intermittent. There are policies that exclude certain other clean energy technologies, in my definition of clean energy technologies, in the international definition, and only have a renewable energy target around renewables. And similarly, in terms of financing those, they have had a prohibition on some clean energy opportunities, including particularly CCS. So really the thing that's been holding CCS back, both here and internationally, has not been the technical aspects, it's been the policy aspects. I won't dwell on this because I go into a little bit more detail, but in the energy space, to make decisions in this, it's extremely complex. I've skated over it, but things like discussing different things depending upon who you are and who you want to, what barrow you're pushing, can give you an apples versus pears comparison. So things like, I mentioned size of the report. Renewables will always talk about, well, we've got so many gigawatts of installed power, but that's not actually what is delivered to the grid. So when people, detractors talked about the N=1 CCS plant, they said, oh, it's too small, 120 megawatts. Of course, it was the first of a kind. But in fact, at that time, it was delivering the same megawatts hours to the grid as the MacArthur Wind Farm, which is the largest in, I think, also in the Southern Hemisphere, let alone, at that time anyway, largest in Australia. So, okay, so it's not actually that small in terms of producing low emission energy. We talk about a thing called levelised cost of electricity. A lot of things you hear about the cost of electricity are using this term. And it's about taking different profiles of capital costs and operating costs to come up with a number. But what happens is that it doesn't necessarily recognise the quality of the power, intermittent power or firm power. So when the LCOE reported for renewables, it's actually intermittent power. They don't talk about the battery power. But for fossil fuels, when they talk about it, it's actually for what I call 24/7 power. So you've got to appreciate that are we talking the same things? Well, in most cases, no. And so on. The CCS itself, and I won't dwell on this, it does actually, because they're larger equipment, existing equipment, you can actually make very significant large cuts in CO2 through an installation of the CCS plant. You can also affect that CO2 from industrial plants, I've told you this, and it also has some other environmental benefits because they're designed to actually take out extra SOx, NOx and ash. So that's a benefit. Lots of research, I've talked about these, and as well as reducing this good power, it also utilises plants that still have a significant life. You can actually still operate them going forward, and it also is one that helps to maintain existing employment. What we need to talk about is a transition to that low emission future. And how do we do that? So I'll quickly go through some comparisons here and say these are a whole lot of different ways you can view. Let's take a different snapshot of how you're going to compare these technologies. I've talked about the power to the grid, and we talk about financing costs. Over time, what are the cost improvements, and so on. I won't dwell on this terribly long, except to say what we've done here is got a common megawatt hours to grid for all of these technologies, based on a retrofit of a brown coal plant into the Latrobe Valley at 90% capture, and how much megawatt hours that would produce at quite a low emissions intensity. 0, obviously, for renewables. A new power plant would be high at 800, a black coal power plant. But these two CCS fitted plants do actually have, not 0, but quite low emissions. And this will be the sort of, these are big beasts. And so this could cost you $1 billion to do this. But it produces it at a cost of electricity, this is the brown coal retrofit, at the lower end of the cheapest intermittent renewable. But it's still, this is 24/7, this is intermittent. Solar is more expensive, and even if you firm it up, it's more costly still. But the thing that's not talked about is actually not cheap in terms of capital cost. To do the same amount of generators and what have you, to produce that same amount of megawatt hours for an intermittent source will be 2.5 to 3.5 times the cost to do it for a CCS retrofit, and even more so if you have firm renewables. That's a bit of a different argument than what you might have heard. Now, don't bother reading this because I've got a prop here. Because for you who reads the paper, I'm not sure how many of you read the Fin Review, but this is an article, that headline, pardon me, which says coal priced out of the market. And it goes on to say how many of these facilities are going to be put in the next little while. A lot of these are firm projects. That's true. So let's have a different look at that and see whether this holds up. This is the quoted maximum capacity, once again, maximum capacity, for about $6.5 billion. What power to the grid, assuming the online time for these materials, it's about that many gigawatt hours. So I said, look, I'm going to create that same amount of power to the grid through different fossil fuel options. Here, a new build with CCS, a retrofit with CCS, or a new build. Sorry, that was without CCS. You find that a retrofit CCS, the one I said before, was about $3 billion. So about half of the cost to do that. You can reduce the power about the same time. And by the way, it is 24/7. This still has some intermittency problems. And even with a new build plant, new black coal plant with CCS would be similar and would have the quality of power better. So it's not as obvious when you read that and the press talking about that in fact is similar. I'm going to skip over this except to say all of my numbers are based on a common financing basis in terms of a weighted cost of capital, etc. But interestingly, a lot of things that are reported in some senses use a very low financing rate and comparing against things that are given very high financing rates. So if intermittent wind has been talked about at $50 to $60 a megawatt hour, intermittent wind, I would calculate that with a 7% return at about that. If you said, yeah, but I'm comparing a new build fossil fuel plant is going to be half the cost of electricity, the wind is going to be half the cost of electricity of that. They're at 60, but if you come over to here, to this, it's getting close to being half the cost. But we're talking apples versus pears. So you really have to be careful about how these things are, you take these on board. And you would say, well, wind is improving really quickly, so we really want to get on board. And this is 2030, and that's a reasonable study, a reasonable assertion. So I've compared, once again, a whole lot of different low emissions technologies, and the CCS technologies are actually reducing as well. So if you look at this space, you can see that the low emissions technologies, CCS, and so on, are actually in the similar sort of band of those improving in the future. And I haven't got the firm technologies. Just look at this one here. So now it's in that space. If you went to a solar thermal, it would be even higher. But in future, these are the sort of numbers it's moving to. Once again, they're not dramatically better than some of the other fossil fuel low emission options. So now we're starting to understand the difference and the apples for apples. I won't, obviously, if you only look on a security basis, fossil fuel wins. If you, the other thing about on security and reliability, we start looking at that. CCS can have some really good opportunities, certainly with retrofit, where these are the numbers you saw in the previous slide, 90, 94, what have you. Well, what happens is, okay, I need to peak, I need more power. I can actually dial back the amount you're capturing for a short time. And by the way, it's cheaper to do less capture. Yes, the emissions intensity goes up, but you can play tunes on that. You can play tunes on that, and tunes on that. And you actually can get more power out of the system. I won't bother going into explaining it, but trust me, you can get the power back in a retrofit when you need it. So that has some real benefits to security. Emissions, sure, renewables win on emissions if you're only looking at emissions. However, they're only good for the power. They don't have industrial emissions, whereas CCS can deal with industrial emissions as well. So, we're talking all these different cross purposes. How does this affect the trilemma? Can you do it in one figure? Up till now, it hasn't, and this is something I developed when I was thinking through this with the Finkel review. How can you actually translate that, all these parameters, into one? And I've tried to do it. Whether it's good or not, it's yet to be seen. But basically, it's trying to look at decision support and how you can actually come up with a better energy technology looking at those three parameters together. So what I've done is I've taken all the quantitative data that you've seen on many slides there, I've massaged them to come up with a single metric, which is equal weight to all of those parameters. And the tool, once again, don't get worried about all these. These are all the different technologies you saw up there. This is a seriatim of what happens to be the best. The lowest on this is the best, all the way up to the least good in terms of how it deals with the energy trilemma. And this is what comes out of it. It says that CCS actually makes a very significant difference to its contribution to the energy trilemma, and most effectively on brown coal retrofit. A lot of people want to shut them down. I think they should be retrofit. The unabated options, the HELIs that you hear about, actually don't improve greatly. because they're actually minor emissions reductions, higher LCOE and no better reliability. You end up with natural gas being useful as well. Firm renewables, which are in this spot here, they get down there, but they're not in the top 5. They're good. But what we're looking at is all of these intermittent renewables, which are at the far right hand of the scale. Oh, gee, that's not right. That's fine. So in fact, the top 5 technologies which actually support an energy trilemma are actually all fossil fuel with various forms of retrofit. And one is not retrofit, it's an NGCC. But this is strange. Where's all the funding, support, investment and all the discussion going in? They're actually going in on the right-hand side of this graph. We're talking about new gas-fired power stations with faster acting open cycle plants that I showed you. Well, they're actually not, they're quite expensive, and that's what's pushing the costs up now. They're actually not very low emission. They're only about half the emission intensity of a brown coal-fired power plant. And we're talking a lot about intermittent renewables. We're getting subsidies for these, and we're even talking about putting in these helis, which actually don't improve things greatly either, if you're wanting to get a trilemma fixed. However, all the ones on the other side, these are the ones that are getting no focus, no support up until now, and they're the ones that actually address the energy trilemma better. Firm renewables are improving, and they're on the horizon, but they're not yet there. So this formulation suggests to me that you should be thinking about how this might be useful in discussions. I've done it for 2030 also. Unabated doesn't change. We get new CCS technologies, those step-out ones I talked about. They fit into the mix. Retrofits are still desirable in 2030. Firm renewables start to enter the top 5 here, but intermittent renewables still stay out there. And so a large number of those top 5 still happen to be fossil fuels, but they need to be done in a low emissions way. So, you can look at it in one dimension. Okay, so something to think about. So what did Finkel do? Came up with his report, 4 key outcomes: increase the security, increase reliability, get low costs down, rewarding customers. Yes, you do need to focus on low emissions now in the NEM. Okay, you've said that. Got to be an orderly transition for plants as they retire, and better planning and governance. Look, it was pretty well received as I saw it. Industry, lobby groups are still saying, yes, this is good. Some hints in the early days about bipartisanship, which I think is absolutely necessary in this space. He included a lot of the features in the submissions. They recommended addressing many of those negative aspects we talked about. They brought clean energy recognition, technology neutral, took away the prohibition of CCS in the CEFC, although that wasn't actually part of the Finkel review, it was announced the week before, and a new clean energy target. The government, as you know, has accepted 49 out of the 50 recommendations. I think very good. CET has been pending, but in truth, there is actually another review underway, what was superimposed on this, called the Climate Change Review. That's not meant to come out with results until the end of this year. And so it's actually somewhat understandable that Frydenberg is saying, well, yeah, we'll keep honing it up. And so that's where we are with that. And, you know, the biggest issue around this energy space is clearly around the political machinations. So I've given you a very, very quick and in some ways intensive overview of this space, and I just leave you with what I think are some of these conclusions out of this. I think the world really has decided we're going to have to go to further reduce emissions, if only as an insurance policy. That CCS is a credible and valuable contributor to that clean energy space, and it's applicable for all fossil fuels. It's not about coal, it's not about natural gas, it's not about biofuel, it's about the CO2 releasing from fossil fuels. The energy comparisons can be very complicated and difficult, and you need some sort of way of getting through these, and perhaps something like a trilemma scale might help, because it shows that there are benefits that can be had from that, and certainly in the CCS space it can actually deliver both now and into the future. And finally, the Finkel review really has attempted to provide a fairly balanced approach to dealing with that, and we await the politics. So thank you, and I'd be more than welcome to take questions. I hope I haven't lost your opportunity to ask some questions. Thank you.
Well, gentlemen, you've had a very broad exposition this morning by Barry. I'm sure there are lots and lots of questions. Yes.
Thanks, Barry. That was most interesting, but to an uneducated person like me, carbon capture seems obviously a great way to go. But is it expensive? The cost of, I mean, I can understand the drill is a once-off, but putting the stuff underground all the time, is that done under enormous pressure, or is it expensive? Or?
Well, the cost aspect is covered in all those areas. The injection costs and what have you were embedded in those LCOEs for that, so that's all been factored in. Yes, it's expensive. Anything in the energy space is expensive. The interesting thing to know about, and the reason why we're down at a kilometre there, is that the crust is full of water, so it's a hydrostatic head all the way down. So as you go down any depth, it's effectively got a massive head of water. So you're down at 8,000 kilopascals or 80 atmospheres, 100 atmospheres, where it's the minimum we're injecting in. But interestingly enough, I mean, this is well-known technology in oil and gas fields and what have you. So yes, it has an expense, but it's technologically tractable.
Roger.
Do you have an opinion on uranium? You haven't mentioned that at all today.
No. Look, my view is the immediate thing we continue to do is contribute to the nuclear power cycle through giving uranium as part of that. I personally think we should also be on the tail end of that and bring back nuclear waste as part of that. And I think there are great opportunities for continuing nuclear power in the rest of the world. I'm still not convinced that we should enter that, because we've got so many other energy options at our fingertips that we can do it cheaper than new power plants.
Graham.
A combined question. Why not retrofit Hazelwood rather than close it down? That's one question. And the second part relates to what Roger said. With atomic reactors, there are breeder reactors being built in the world, but the technology is not up to it yet. Now these breeder reactors don't produce very much byproducts at all, and it just seems to me we're avoiding the elephant in the room, and that's atomic power.
Agreed. I mean, things like the pebble bed reactors, which are very small modular reactors, rather than going to a 1,000 megawatt one hit, would be a great opportunity. They're much more intrinsically safe, and we should keep looking at that. But I just respond with, at one of the Finkel technical sessions, someone got up and asked a question about that, we're not talking about the elephant in the room. His comment was, the elephant's not even in the room, in the context of that discussion. And it's largely because we don't have, the prohibitions and legal reasons why that's not the case. But I mean, as I said, we're still in the nuclear power cycle, and should be, in my view.
Yes, David.
Barry, what is the capturing the carbon underground? Does it have any effect on the water table?
There are about a dozen parameters that have been analysed in terms of the geomechanics, the hydrology, the geochemistry. All of those things have to be addressed when you're selecting a site. In the case, I project managed a study back 10 years ago now in the Latrobe Valley, looking at large-scale injection into offshore Gippsland Basin, which has progressed, and there is a government authority that's looking at that as we speak. And a very interesting thing with the water table in that part of the world is a massively open sort of water flow. You're getting all this water going offshore, basically. And a lot of it's being, and there are a lot of flows around production of oil and gas offshore, the actual mining, the coal, agriculture, really quite have changed those balances of the water heads and what have you. So yes, it's absolutely something you need to look at, but it's not actually going to affect potable water supply because we're so deep. We're not, because we should be separated from the seals, which might be at a kilometre, where you might be getting water from wells and stuff is so far. But they all have to be looked at.
You won't get free soda water then.
In that regard, do you get acidification in that environment?
Which is acidification?
Yeah.
Yeah, look, that's where the geochemistry you have to look at. Some reservoirs, there are things like in Saudi Arabia, the various limestone deposits and things that are in the subsurface. So yes, there are some issues sometimes about whether it will affect other minerals and so on. But certainly the ones that I've been involved with here in Australia, there's been no particular evidence that would create any more than what we would expect.
Could they could you use the CO2 for fracking to drive the gas out of the natural gas out of the rock?
Yep. There's been work on actually using CO2 for what they call enhanced coal bed methane.
Yeah.
So the coal bed methane, the methane is connected to the carbon, and what you put the CO2 in, and preferentially the methane is released, and the carbon locks onto the carbon, and that can actually produce methane. So I expect it could well be used in Queensland associated with the natural gas production there. And certainly CO2 also has been looked at in terms of a physical use. It certainly has been used for enhanced oil recovery. Some of those things, and it also enhanced gas recovery, where you're repressurising a reservoir.
Barry, you mentioned fixed renewables, and that I didn't get it, but I take it that you mean to provide energy storage, i.e. major batteries, to store renewables for the off-generation times. And I think this comes back to the involvement of battery storage, and that's the big unknown in the whole of the equation at the moment as I see it. I think the time and the cost to produce batteries and windmills and panels and all of that kind of thing is intrinsically a shorter time than producing a full-scale coal-fired power station with CCS. CCS is roughly half the cost of a combined station. So there's a big difference here in time and probably in cost, and anything that takes 5 or 8 years to build is going to be more expensive before you get in a return on your capital. So are those things included in your analyses there of the time to build something and getting a payback on it?
Yeah, certainly in the LCOEs, all of those firm renewables incorporated battery cost improvements over time, inverters, because you have the batteries but you also have to buy an inverter, which is the extra cost and probably the more expensive part of the cost, and so on. But in terms of the big win, well, that's a sort of double-edged sword here, the big win is that if I can go and retrofit, and you mentioned Hazelwood, I didn't actually address that, but if you retrofitted Loy Yang A, for instance, or Loy Yang B, you would actually get incredible immediate reductions in CO2. Whereas if you had to get the same amount of reduction in CO2 through renewables firmed up, it's much more expensive, even when you counter the improvements in cost. So they go in maybe 100 megawatt slices, but you need 100 megawatt slices or something like that. So each of those projects.
One more question.
Yeah, I'd like to ask this. When I go back to Scotland, I see that a lot of the hills scarred by windmill things, you know. Since I understand a lot of taxpayers' money's gone into funding each of these windmills, is there ever an audit done on the performance of, say, any individual one? Is the performance that they, how much electricity they produce, ever available to be seen by the public?
Well, certainly in Australia it is. You can get that sort of detail from the NEM, from the AEMO or whoever, the market operator. I was reading something yesterday that talked about the coincidence of the maximum capacity of, say, a wind farm, coincident with the maximum need for it in the NEM, is something like 7%. It's very, very low. And so you have a real probability, but certainly the actual performance of a given wind farm, yes, that's certainly in Australia you can get that.
Right. Excuse me, what did that mean though? The 7%, I didn't understand.
Well, it sort of is the fact that you, when I say it's only available 30 to 35% of the time, you know, if you had it, that when you actually need it in terms of providing the reliability to the NEM, do they provide that support at that capacity? It's very, very slow, very, very low percentage of time.
So do you still think they're justified?
Well, look, I think they're part of an overall low emission, but one of the biggest problems I think with the NEM is the way we've got pricing the system. It's been priced on the basis of a base load with intermittent peaking plants. And we've now got a situation where with all the incentives, say a wind farm that might be generating on my 7% return basis about $80 a megawatt hour. They don't get 80, that's what they would get a good return on their money. They get the NEM price, which might be $100 to $120, plus they get the renewable energy certificate, which at the moment is around $78 a megawatt hour. So they actually get, when they could be okay at $80 a megawatt hour, they're actually getting probably close to $200 a megawatt hour. And it's useful, but I think there's a time where we have to change. As Finkel has said, we now have to put into a region firm renewables if we're going to put renewables. So I think it's been a transition to get a technology in. The technology has improved, but it's improved so much it doesn't need that incentive anymore. There are other technologies that probably do need that incentive to improve, and CCS is probably one of them. And firm renewables is also another. Batteries and things. So it's just this is all about a transition that's really a problem dealing with.
Any further questions? Barry's staying for lunch.
One quick one, tidal power, it's reliable. No one's done anything about it since the French.
Oh, that is Garden Island, Western Australia. There are a number of tidal companies out in Australia. But once again, they're very, very small contributors. It's sort of like maybe a megawatt or 2 megawatts, probably only the same size as one wind turbine. Yes, it's 100% available, a very high percentage available.
I'll ask David Seachman to propose a vote of thanks to our speaker.
Well, firstly, Barry, thank you very much for your very informative talk. Certainly in the short time that you've been able to give the talk, you've embraced the climate change right through to the CCSs. And I'm certainly more informed, and I'm sure my colleagues here are more informed, because every day we're bombarded with climate change and political people pushing and shoving in different directions, and it's quite confusing for us all.
Yes.
However, it was good to see at the G20 where the majority of the world was supporting what you're promoting. I believe, except for America, which is staggering indeed. But I certainly have a better appreciation of, especially with the CCS push. And I think we need to be conscious of the fear factor that's going around the world where they're pushing very heavily for renewables, they're ignoring the fact that they need a base load to start with. And I think your retrofitting program is quite encouraging. So thank you very much.